All right, so my name is Phil.
And I'm Mike.
And we work at Rackspace. You may have heard of us. We host a few servers, 100,000 servers. And we're going to talk about our experiences building a polyglot app using Rails and Erlang. This isn't going to be an Erlang tutorial, but we're going to show you just enough Erlang so you can look at the code and know what we're talking about. So with that, I guess we'll just get started. So the problem, part one. So I started at Rackspace about 2 years ago. And there was a significant problem when I started. And that is we had 20,000 network devices that needed to be managed. And those devices are in 9 data centers across 3 continents, North America, Europe, and Hong Kong. All of our stuff runs from a DC in Virginia. We have high latency links to London and Hong Kong. And we have 5,000 devices in London. So it's not like these were a small number of devices that needed to be managed. So these devices, we're talking about firewalls and load balancers. They pass traffic like a pro, but they're not designed for high throughput management. In fact, managing most of these devices means SSHing into them and driving an SSH session using expect, which, as you can imagine, is not very fast.
Yeah, I wanted, one of the things about those devices and about SSH is that we've got, I mean, these are probably most of the firewalls that have been bought for the history of Rackspace. So while some of the newer devices have more robust management APIs, many of the older ones, and that comprises most of the devices we're talking to, are designed for use by small to medium businesses. So that's usually their, the problem they're solving for that product is usually just, your network admin SSHing in and issuing some commands. The idea that they're going to be configured in parallel at the scale that we're working at just didn't enter into the product design discussion.
And the problem is that, of course, we needed a high throughput solution. We have to back up all of these devices every 24 hours. We have to update these devices, and all of these things, of course, have to happen during off hours for the DC where the device is located. So if it's in London, that means we run our backups at 7 o'clock Central Time and not in the middle of their business day. And the time we spend in I/O is the primary bottleneck, communicating with all of these devices. This is one of those situations where we're hard bounded by network I/O. And so that means that if you want to speed things up, you got to talk to more devices in parallel.
Yeah, so this is an interesting point here, is that I think oftentimes now when we think about parallel computing, one of the things that comes up is the ability to parallelize computation. The problem we're dealing with here is not one of parallelizing computation. It is of parallel access to many different things. And you can see that factors in heavily into the solution we've come up with.
But we also had another problem, and that is huge blobs of data. We have lots of devices, and they produce lots of data. So lots of backups equals a big database. The system that was in place when I started had a 260 gigabyte MySQL database, and almost all of that was in one table. So there are things you could, so at the time we were saving a backup from the device every night regardless of whether the configuration had changed or not. So obviously there are some optimizations that we could do to reduce the amount of data we're storing, but even still, with the number of devices we have and with the fact that, even a relatively stable device is going to have to get changed every once in a while, we still have a lot of data.
And we also, I think that, I think that Phil mentioned, we do some things to reduce the amount of data we have to store, except considering some other constraints we have, we don't want to be too clever about deduplication. It's best to keep these things more or less as blobs that are easily accessible.
And ad hoc searching is difficult but important. We have to we have to be able to look through this information very quickly and find certain pieces of information. I'll give you an example. We had a certain load balancer vendor that had a flaw in their SSH daemon that it was a security vulnerability. And so we needed to know how many firewalls had a load balancer behind it that might have been vulnerable and allowed SSH access to the outside so we could go through and close that up. And that's something that with the old MySQL database, because it wasn't indexed properly, that query probably would have taken all day. And we didn't have all day to run it in. Of course, the point of doing the backups is that eventually, devices die and you have to restore them. And we have SLAs with our customers, which means that we have a limited amount of time in which to restore that device. So the techs need to be able to get access to that information, pull that configuration out, and load it onto the device as quickly as possible. So we need to have fast, reliable access to that data. And we have to generate events every time we touch the device for auditing purposes and standards compliance and all of that, yada, yada, yada. We have to know when we touch a device. And we touch devices a lot. So we have to keep that event information around. And one of the problems we ran into with MySQL, as I mentioned earlier, the table wasn't indexed properly. We said, oh, we can do that in a migration, except that once we tried to add that index, it literally killed the database. It fell over.
I think that at one point in time we were looking at like an epi-cycle for indexing things. And so at that point, I'm almost like you're going to want to throw your hands up in the air and just start searching for different employment.
The rigid schema of relational database made adapting to new devices difficult. Each device type has different properties. We have firewalls, we have load balancers, we have IDSs. We want to keep track of different attributes of each of these devices. And of course, backup means different things for different devices, particularly when you start talking about different vendors. Sometimes it's just a snapshot of, a couple of hundred lines of configuration commands. With the F5 big IP, it's a big zip file with all kinds of who knows what in it. And we needed to be able to keep all of that information in a reliable way, and then, as I mentioned earlier, be able to serve it up to the tech so that they can get at it quickly. And of course, we needed to grow with the business, right? Rackspace is a growing company. We're adding devices every day. We're actually we've added some new vendors since I started, and we have to be able to keep up with that, right? We can't say, oh, yeah, I understand we've got this new vendor, but it's going to take us 6 weeks to figure out how to back it up. That's not acceptable.
So to add some context to that, in 2009, we had approximately 17,000 network devices that we were backing up, and this is primarily firewalls and load balancers. Now we have about 21,000. So 2 years at 4,000 devices or so, and that rate is probably going to increase in the future.
So the solution that was in place. Before I start, I'm not digging at anybody, right? This was a solution that worked at the time, and we grew to a point where it didn't work anymore. But it was basically multiple Ruby apps, some Rails, some scripts, and there was overlapping areas of responsibility. So we had 3 applications that all talked to firewalls in slightly different ways. So this made it difficult to change, right? So you find a flaw in your methodology, and now you got to go and you got to touch 3 different applications that are all slightly different and figure out how to fix that flaw in each place. And we also ran into some scaling problems. The concurrency was done using Ruby 1.8 threads. It was an I/O-bound problem. Threads block on I/O. I think the rest is pretty obvious. And we also ran into some serious performance issues with the version of expect that ships with Ruby 1.8. It analyzes the input stream 1 character at a time. It's ridiculously slow.
Yeah, no, I was just going to point out that, honestly, I think that, expect at RB, you'll hear us complain about it a lot. For the environment I think it was written in, or written for, the going 1 character at a time and matching on that makes a lot of sense. But when you're, again, hitting 15, 20,000 devices, that one character string search at a time becomes a really naive algorithm to use.
And we did look at vendor device managers. There are some problems with these. Of course, they only work for the types of devices delivered by that vendor. Typically, it's a small number of devices per manager. They're expensive. We needed a solution that would work with every device we have in our data center. And nobody makes that.
Yeah, to kind of put that in context, I mean, you'll get like a big corporation, right? And let's say they have 500 firewalls, right? And so you might buy 2 instances of an enterprise device manager from Cisco or F5 or something like that. Well, when you go to one of these guys and you say, okay, well, we need to manage 15,000. Well, then their eyes turn into the dollar signs, right? Because it's like most places just don't have problems at this scale.
So we implemented a better solution. We have a Rails application on the front end. The back end application that does all the talking to the devices is written in Erlang, and we're storing everything in MongoDB. We're fully buzzword compliant.
Yeah, we were a couple years ago. Now we need like CoffeeScript in there. So sorry, let you down.
So what we're going to talk about today, we're not going to talk so much about Rails and MongoDB, because hopefully everybody in this room knows what Rails is, and quite frankly, our Rails application is not that interesting. And MongoDB, quite frankly, we just set it up and started storing data in it.
Yeah, I think that we might be like the only 2 Rails developers in Texas who have had a good experience with MongoDB. I mean, the impression that we get, honestly, is that like, oh, that it eats your data, that there's certain collection names that just route things to dev null and don't warn you and stuff like that. That's not been our experience. We know new limitations going in and have been paid attention to them. And we've really had no problems.
So we built the simplest thing that could possibly work, right? I mean, you hear this all the time. This is one of the Agile principles, but it was something that we really took to heart. We're a small team.
That's no one. Can you save your question for the end?
Okay.
Or do you, I mean,
What's your question?
The question is, since you're using Erlang, why did you choose Mongo instead of Couch?
So the question was, since we're using Erlang, why did we choose MongoDB instead of Couch? So there's basically 2 answers to that. The first is we weren't using Erlang when we chose MongoDB, and secondly, overall we felt that MongoDB was a better fit for our problem than Couch was.
Yeah, I mean, like from my point of view, honestly, this is a decision that was made before it came on. I'm not to throw Phil under the bus or anything.
It's very comfy under this bus.
We've had no problems with it. But from my exposure to Couch, honestly, I think that its focus on like the views and distributed map reduce and stuff, that's not really the type of operations that we're performing on this data. Honestly, like when I look at Couch, I think like, okay, this looks really, really cool, but the programming paradigm is something that we'd have to get used to, that we'd have to learn. Whereas with Mongo, it's like, oh, okay, well, it's kind of enough like MySQL or Postgres that I can, fib it until you really know it. And so that I think was one of the big selling points there.
One of the things you...
Thank you.
Oh, you're welcome.
One of the things you won't see is a message queue. It just wasn't something we really felt we needed at this point. So we run a lot of batch jobs in our Erlang application, and the jobs that are initiated from the Rails app, we just store those in MongoDB in the Erlang application polls. And then the jobs that get run at the same time every day, we have a configuration file, and we just store that in there. And we have really very few writers to the database. The Rails app is very read heavy, and the Erlang application basically does almost all of the writes. And one of the really nice things about MongoDB is you can do atomic updates to documents. And that's what we do. Almost all of our writes to the database are atomic updates of documents, updating a counter or a status field or a backup field, something like that. So this is what our application architecture looks like from a very high level. We have our Rails application here. There's our Erlang app. We have a RESTful API that sits on top of that. MongoDB there in the background, our little network devices down here. And we actually have some other clients within the company that talk to our REST API.
Is anyone here a Rackspace customer? Oh, good on you guys.
I knew there were some smart people in the audience.
Do you ever use the Rackspace portal?
My Rackspace?
No? My Rackspace? Nobody? Okay. If you go to manage your firewall devices from within that, you're actually talking to this REST API.
Yes, the firewall manager in the My Rackspace portal talks to this. So, Erlang. How many knew what Erlang was coming into this talk? Okay. All right. How many of you have Erlang code in production? Yeah.
He works at Rackspace, by the way, so it like doesn't even count.
So we're just going to give you a brief history of Erlang before we move on. So Erlang was invented at Ericsson Computer Science Laboratory by this guy, Joe Armstrong, in 1986. In 1988, Erlang escaped the lab and was used in actual telecom hardware at Ericsson. And in 1998, it was released as open source. Probably the most famous Erlang product ever is this HD301 ATM Switch. It was built for British Telecom. It was about 1.5 million lines of Erlang code, and it went through a 2-year evaluation. During that 2-year evaluation, they achieved 9 nines of uptime. I'm just going to put this up here in red and let that sink in a minute. 9 nines of uptime. That's ridiculous.
I don't even think that they like count sigmas that high.
How many seconds is that?
A very small number.
We debated, had we known you, sir, were going to be in this talk, we would have figured it out. We debated this, like somebody's going to ask, like how many seconds? And we're like, I don't know, like it's a lot.
Now the thing is, Erlang doesn't guarantee you 9 nines, right? I mean, this is certainly an exceptional product. But Erlang gives you the tools that you can reach 5 nines or whatever it is your target for reliability. So Erlang is a functional language. So it's got some core concepts a little bit different from the imperative OO languages we're used to. It is dynamically typed, so in that respect, it's very much like Ruby. One way it's very different is this concept of single assignment. Once you assign to a variable, you can't change the value of that variable. Now, this is one thing that a lot of people complain about, quite frankly. And it's really not that bad. Variables are scoped to a function, right? So if you keep your function small, in general, it's not going to be a problem.
And you guys just keep your method small, right? Right?
So this is an example. In the first line, we're assigning the value 1 to the variable a. Erlang statements are terminated with a period. And in the second example, we try to assign 2 to the letter a, and Erlang throws a bad match error and says, nah, you can't do that. So the trick here is that the equal sign in Erlang is not an assignment operator, it's a pattern match operator. And it just so happens that the behavior of the pattern match is that if the variable on the left-hand side is not already bound, then it's bound to the value on the right-hand side. And this allows some very cool pattern matching.
Can I jump in for just
yes,
a second?
yeah.
I know, because so like Phil's been using Erlang, how, 4 years?
Yeah.
Something like that. I've been a year, right? I think this is my 53rd week at Rackspace. So I had gone through some Erlang tutorials before I came, and I was like, oh, excited and all that stuff. And single assignment was one of those things that I was thinking to myself, oh my God, how do people live in this world, where you can't change, that's not true. That is, out of everything that I thought Erlang would be like, and it would take some getting used to, that was the first thing that I just forgot about. It's at the point now where when I write Ruby, sometimes, yeah, I will terminate expressions and periods, and Rails, Ruby does not like that. But I will find myself mistakenly thinking that I can only assign to something once in Ruby. It's like it feels natural, to the point that I'm saying, like, wow, this is just, that it feels to me like Erlang is enforcing something that in most cases, you should just be obeying as it is. And
in this example, we assign a list of 3 numbers, 1, 2, 3, to another list that has 2 variables and a literal. And the result of that is that we have B and C that have the values 1 and 3 in them, exactly as we would expect. And the 2 matches. If we had had B, 3, C, then we would have gotten a bad match error and it would not have done the assignment. And as you can see in the second and third lines, we can say b equals 1, and it just returns 1 because we're pattern matching. We're not assigning. And we say b equals 1, and Erlang says, yes, you are correct. B, in fact, equals 1. Another thing that you have to watch out for is immutable data structures. So you have all of these rich data types in Erlang, but they are immutable. So that means when you change them, you get a new copy of that data structure. And a lot of people say, oh my God, isn't that terribly inefficient? And in fact, it's not. And this book right here, Purely Functional Data Structures by Chris Okazaki, this guy is a computer science professor at the Army War College or something like that. But this, basically, a large chunk of the Erlang standard library is based off of this book. And he goes into excruciating detail about why immutable data structures aren't slow.
And does anyone know like the one huge practical upside about immutable data? Right, exactly, right. And so it's not like this isn't Erlang or minimal state, right? I think that Clojure nowadays is like the new hotness that is really exposing everyone to this idea. But Erlang's a very pragmatic language, and this reflects that, right? Like I think that they have all this immutable data in there, honestly, because this is one of those decisions that makes the parallelism and the concurrency possible.
So.
Right.
Yes.
Exactly.
Yes. Mm-hmm. And here we have an example where we're creating a new dictionary, and then we're assigning 2 values to it. And it's in the second line, the first parameter is your key, and the second parameter is the value, and then the third parameter is the dictionary that you're changing. And this is one of the things, if you go out and you read stuff by like Damien Katz, he'll say, oh my God, this is terrible, because look, I have to put numbers after the variable name. The thing is, if you see this, if you see D1, D2, D3, D4, you're probably not doing it right.
It is that is a code smell.
Yeah. And in fact, there is a much better way to do this particular code. You can do this.
Yeah, honestly, like as I've been learning, half the times I'll do things like the hard way, and I'll have like D1 through 5, and then I'll look at the standard library documentation again. It's like, oh God, they wrote a function for that. That's just part of the learning curve.
As we mentioned, it's concurrency oriented, and this is not a add-on. This isn't a library. This is built into the language. Everything about Erlang, from the very lowest levels of the VM all the way up, is oriented around concurrency. So we got 2 more little code samples just to kind of show off here. This is the bog standard factorial function, the hello world of the computer science. We declare a module called fact, and we export one function called fac. And in Erlang, function signatures are identified by the function name and the arity of the function. So our function fact takes 1 parameter. This function has 2 clauses. The first clause pattern matches the parameter on 0, and if that is the case, then it just returns 1. In the second clause, we take the parameter n and we multiply it by the value of fac n minus 1. And you will see a lot of recursion in Erlang.
So yeah, the tail recursive functions are optimized. So
yes, it's very cool. Here's a slightly more complicated example. This is a quicksort, and in this one we also see. So we see 2 very cool things here, right? So we've got two clauses as before. As before, the first clause is our terminating clause, and it takes an empty list as the parameter and returns an empty list. But the parameter to the second clause is very interesting. What we're doing here is we're taking a list and we're breaking it down, and we're saying we want the value of the head of the list in the variable pivot, and the rest of the list in the variable rest. This is what we used to call destructuring bind in Lisp. And you can do a little bit of this in Ruby, but this is something that you do a lot in Erlang.
Probably the famous example is if on Ruby you have like A, B equals an array that contains 1 and 2, A will receive 1 and B will be bound to 2. That's destructuring bind in Ruby, but that's pretty much as far as it goes.
The other interesting thing here is that when we call quicksort recursively, what we pass through is a list comprehension. And list comprehensions in Erlang, quite frankly, are a little bit hard to read. I typically read them from the middle out. So the first one is we want to take every front from the list rest, where front is less than pivot, and return front. And in the second clause, we say we want to take every back from the list rest, where back is greater than or equal to pivot, and return back. And this is basically a very shorthand way of doing a map.
Yeah, I think that list comprehensions, some people like them, some people don't. In most cases, you can perform the same thing using like more traditional like module function names, stuff like that. I know that in Ruby, like we don't have list comprehensions, but we do have the awesome, wonderful enumerable mixin, so that takes care of a lot of it. Maybe if you come from Python, you might have more exposure to this.
So we're going to talk about the details of two particular features of our Erlang application. One is the batch job framework that we use to execute these backups and these updates of the devices. And the other one is our RESTful API and the web machine framework, which is the bee's knees. So the job framework is basically consists of a runner which fires up a number of workers, and then these workers use a callback module to do the real interesting stuff. So the runner and the workers are a framework, and the callback module is what has your actual logic for the job. The communication between the runner and the worker is very interesting. So what happens is the runner starts a worker, and this is the worker's an Erlang process. It's a lightweight process. It runs entirely independently of the worker. So the runner starts the worker, and the worker sends a message back saying, "I'm ready." At that point, the runner pops an item off of its internal queue and sends that item to the worker saying, "Process this item." And the worker then says, "Well, you know, I'm just a worker. I don't know how to do that." So it calls the process function on the callback module and waits till that is done. It doesn't care what happens, right? Just that it's done. And then it returns ready to the runner, where the process repeats itself until there are no more items in the queue. And when the last item gets popped off the queue, then the runner sends stop to the worker, and in this way the workers all end up being shut down.
So in this diagram, right? Like, so are runner and worker in the same process?
No, runner and worker are different processes.
What happens when the worker process crashes?
Well, see, the runner is monitoring the worker process.
and this ultimately is, I think, the reason why Erlang was the right choice.
Yes. The runner is monitoring the worker process. And so what happens when the worker process crashes, because we do something stupid, as we occasionally do, then the runner gets notified. It gets a message that says, "This process you've been monitoring has crashed." And it cleans up, starts a new worker, and keeps going.
Has anyone done any like inter-process communication with regular Unix, like POSIX or POSIX processes? Yeah, did you enjoy it? I mean, you know, it can be done well, right? It has been done well. But you have to, there's nothing that's really built in, right? It's sort of like you've got all the what do you say, the plumbing and not a lot of porcelain.
Yes.
Erlang provides that porcelain in a very elegant and very easy to use and easy to comprehend interface.
So I'm going to show you a couple of code samples from this jobs framework. I'm not going to linger a lot because we're kind of running short on time here. But in Erlang, Erlang's version of an interface we call a behavior. And so we've defined a behavior that we call a job. And the way you define a behavior is you just implement a function called behavior info and return a list of function names and arities. And then whenever you compile your modules, when you say this module conforms to this behavior, the compiler will check that and will yell at you if it doesn't. In this case, anything that is a job callback has to export an init that takes one parameter, process item, which takes 3, worker died, job stopping, and job complete, which are all notification callbacks when the thing happens. So this is a piece of code from the actual runner. This is the event that gets processed when one of those workers sends a worker ready message. And we just, so the little s hash state there, that is an Erlang record. It's like a struct, but you have to specify the name of the struct every time you reference it because of weird historical Erlang bullshit.
Yeah, we know no one likes that. Okay, so just you have to accept it and move on.
So the list of things that we need to process is called items. We pop that off the queue. If the queue is then empty, then we stop the worker and we transition into the complete state. This is a finite state machine. So we transition into the complete state and return a new process state with an empty list of items. If we actually get something off of that queue, then we call job worker process, which is that worker process we discussed earlier. And we pass in the PID, the item we want processed, the start time, and a piece of state that we will carry around for the worker. And then we call next state running, which basically keeps us in the running state. And we pass in the new list of items, which is now one less than it was before. So this is the code that we were talking about earlier. When a worker process goes down, this function gets called. And we have the PID, we have some crash information. So we can then, in this case, we clear the worker. And then we call the worker died callback and start a new worker and keep going in whatever state we were in before. The interesting thing about this, you see that we call the spawn function. And spawn is what creates a new process in Erlang. And it takes basically 3 parameters: a callback, a function name, and a list of parameters. And it's like an apply or eval, which you will see in other languages. The interesting thing here is that the module name and the function name have to be atoms. But as you can see, we're passing through the callback as the module name in a variable. And you can actually call functions on a variable name, because these variables are just really very thin references. So anywhere you can use a value in Erlang, you can use a variable holding that value. And that even applies when you're calling functions. And then the last piece of code here, this is from the actual worker process. And this is the code that gets called when we are processing an item. So when that process item message gets sent through, we wrap this all up in a try-catch block, right? So that if the callback throws, we don't care. So we call process item on the callback module. And then when that's done, we send the worker ready message back to the runner. And there's no need to reply because it was all done asynchronously. So quick story time. We had a situation a little while back where our production instance of this application was deployed on 2 VMs, and one of them kept crashing. And we couldn't figure out what was going on. And ultimately, after doing a lot of testing, we figured it's got to be something about that VM. And so we, in casting about what to do, right, we can't accept downtime. So we moved all of the responsibilities for that node to the second one. And then we, reinstalled the first machine from scratch. But at no time did we ever have to deal with a job being down. And we actually were able to increase the number of workers. We doubled the number of workers on the second node, so everything ended up completing in the same amount of time anyway. And that was very cool.
Yeah, whereas usually, the load is distributed among 2 machines at this point in time. Well, one went down, so we're just going to move everything to the other one, and you don't have to sweat it. It just happens, and it works very well. So now we're going to get to the RESTful API. Now this is made with Web Machine, and I'm not sure if anyone in here has heard of Web Machine before or has played around with it. It is a little bit, you can kind of think of it more like Sinatra or maybe Goliath in the Ruby world, but it occupies about the same position in architecture, in our architecture, as Rails controllers, but it really exposes you to the details of the HTTP request response lifecycle. And I say that because, as I guess is a way of introducing the subtitle there, which is that in essence, when you're writing code with Web Machine, you're basically developing a custom web server for your application. And for all of those places where you don't want to override a particular bit of behavior, Web Machine has sensible defaults. It really applies that convention over configuration mentality to really the raw elements of the HTTP request response lifecycle. And so it's got a lot of details, right? And you can see exactly, oh, can you see that?
There's going to be a test over this, by the way.
Yeah. I'm not sure how well you guys can see that, but I've got the address
Probably not
on there.
very well.
If you go to webmachine.basho.com, you can see the state diagram. This is exactly how Web Machine sees an incoming request. And at virtually every point in that cycle, you can override a callback to basically say, oh, no, it's, choose your own adventure applied to web programming. And you can say, oh, no, don't do X, do Y. Web Machine really allows you to express your API in the terms of HTTP. It's very, very cool. And so that leads to the next point, which is that if you know HTTP, Web Machine is really, really simple. If you, I don't think anyone in here would ever do this, but if you were ever like, maybe didn't care so much about HTTP because Rails controllers, for example, hid that from you, then there might be a little bit of a learning curve. But if you're familiar with the protocol, this is going to be right up your alley. And you can really see it as my ad hoc measurement here is that the number of types of things you have to learn is actually pretty low. There are 3 important types of things in Web Machine, right? Dispatch rules, pure data, right? Resources, they're just composed of simple functions, and then requests. Now, when you look at a dispatch rule, it's kind of like a dispatch rule is kind of like Rails routing. It basically says, so you got a tuple there, and it has 3 elements in it. The first element, that devices and server, that basically is matching a URL. In this case, it'll match, as in the example below, that get devices 1, 2, 3, 4, 5, and the server atom or variable will be bound to the value 1, 2, 3, 4, 5 in that URL. The second element is the resource that you want to handle the request, and then the third are default arguments to the resource. Now, so when a request comes in that matches that dispatch rule, Web Machine inspects the resource module for defined callbacks and just starts calling them. Now, a resource is it's a plain old Erlang module. It's composed of largely referentially transparent functions. That's like a complex way of saying like it's simple interface, right? You get 2 or 3 parameters in, and you pass basically 3 out. Really easy. There are functions defined or callbacks defined for every part of that life cycle. For example, and there's about 30. For example, you have resource exists, and if you want to control whether a Web Machine will send a 404 or a 200 OK, you can override that. Or you want to control authorization, override is authorized, and it'll get called. So here I've got examples, kind of completely contrived examples of resource functions. You can see at the top there that resource exists function, which is a permanent 404. So you can see it's called with the request in the context, and so the request is the request data, much like Rack request, and the context is just like a bag of information. Functions can put stuff into it or pull stuff out, and you can use that to carry the state between one function call to the next. And this case just returns false. That's the response, right? So resource exists, false, no, 404. So permanent 404. And so the second is authorization, implemented in the worst way possible. Basically what that does is that it finds out the number of seconds that have elapsed since midnight. And if that is an even number, you can get in. And if it's odd, then you have to try to make another request. So there's resource functions. I don't recommend using that
in production.
Yeah, no, don't do that. So then we get to requests. And like I said, I think by this point in time, you're already pretty clear about what a request is. It is first argument to each resource function. It's got a simple getter setter interface, and it's just like the stuff you want. Like you get the call to peer function, you get the remote IP, you can set headers, you can do all sorts of stuff like that. Real straightforward. You can just write these resources that are composed of these callback functions, and you just define the interface that you want your application to have. Here's a slightly more complex one from that firewall API. The content types provided this is the function that Web Machine calls for you to determine which content types you provide to clients. There's an analog content types accepted, but if you want to see all the details, you can go to the Bash Show website. And then you can see here on the first line it says types, and that is application/JSON, and then it returns that atom. Now that string there is for the purpose of the client, for the edification of the client. The second one is for Web Machine. And so basically what it says is that you say, okay, we provide this type. The client says, oh, okay, well, I want that type of data. Then Web Machine calls a toJSON function. And down underneath it, we've got we've got an example of that toJSON function. Basically right there, you just get the current device, and that's just a record, in this case, MongoDB record actually. Get the user ID, and then talk to the device and return it, successful or error, whatever you want. And that's pretty much Web Machine in a nutshell. You could go out and be productive with it right now.
So if you do go out and decide, hey, I want to look into this Erlang, we wanted to warn you about a few things that we learned through blood, sweat, and tears. And the first is the primitive obsession. Erlang's types feel very low level compared to Ruby. You can get a long way in Ruby with string array and hash. Erlang doesn't have any sort of literal hash or dictionary structure, and strings are a little bit different.
Yes, they are. Strings in particular. So strings in Erlang, you want to think things that are string-ish data types. I'm going to gloss over some of the details here. But if you start programming in Erlang, learn about I/O lists as fast as you possibly can, or else you're going to be sitting there thinking like, oh my God, string handling is impossible. It's not. You just have to do it the Erlang way.
So a string in Erlang is basically just a list of integers for which each one corresponds to a Unicode code point. The quote marks in Erlang are there to deceive you. It really is just a list. There's also a data type called binary, and that is the second example here is a binary, and that is just a bunch of bits that in this case just happen to form a string. Erlang, you use binaries in Erlang to do things like represent TCP packet headers and stuff like that.
Yeah, if you're like into low-level programming or anything like that, you can do destructuring bind and pattern matching on raw binary data. It is really, really, really cool, but we don't have the time to go into it.
But this last example is what we call an I/O list, and basically an I/O list is a string or a binary or a character or a deeply nested list of any of those things. And so here we have a list that contains a binary, a list of characters, and a string with a Unicode character in it. And any Erlang function that does I/O, you can pass this to that function as a string, and it will make a string out of it. So a lot of people, they fall into this trap when they're programming in Erlang of trying to build strings. Don't. Just create a list with all the elements you want and pass it through. So we're running out of time, and I'm going...
Wait, no, go to this one.
Yes.
OTP.
Don't use the low-level Erlang concurrency primitives. Use OTP. There's no excuse. This is an excellent book. Go buy it tonight.
Although the one caveat on that is that using OTP without understanding the concurrency primitives is like using an ORM without understanding SQL. You have to understand what you're working with.
So this is us. I'm Phil. This is Mike. Go to speakerrate.com and rate the talk. And if anybody has any questions that we don't have time for, we will be around for the rest of the day. So come find us, and we're more than happy to talk.
Bye. Have a good day.